Welcome back to the deep dive. Today, we're peering into the very near future of software engineering. We're talking about these LLM-powered software agents that are already starting to really boost developer productivity.
They absolutely are. But there's a huge problem on the horizon, and that's, the core of the source material we're looking at today.
Right.
See, current agents are incredible mimics. They learn from human data GitHub issues, bug reports, perfect test suites, and that reliance on clean human-labeled data, well, that's the barrier. That's what's stopping them from reaching, true superintelligence. We just can't scale that kind of human effort forever.
Okay, so let's unpack that. If the agents are running out of human-made homework, the mission is to teach them to write their own.
Exactly.
And that's what this deep dive is all about. A training paradigm called SSR, or Self-Play, SWERL. We're getting into how a single LLM learns to generate and then fix its own increasingly complex bugs all by itself.
And the core idea is just, it's so elegant. It's adopting that self-play dynamic we saw with systems like AlphaGo Mastering Go. But instead of a game board, the learning is grounded in these massive, messy, real-world code bases.
So it's making its own challenges, tailored perfectly to what it needs to learn next.
An infinitely scalable curriculum, yeah.
That's the key right there. So let's set the stage. What does this SSR process need to even get started? Because this is where this source material gets really, really interesting. The assumptions are surprisingly minimal.
Yeah, a key design principle was minimizing prior knowledge to almost zero. It really only needs one thing: access to a corpus of sandboxed environments.
And what does that mean in practice?
It's just a pre-built Docker image. It's got the raw source code and all its dependencies installed. And that's it. Literally, that is all it gets.
Wait, hold on. So no existing test files, no documentation, no natural language descriptions of what to do.
None of it. It assumes no access to any of that. It doesn't even know what programming language it's looking at or what test framework is being used. The agent itself is responsible for discovering how to run the tests and then how to parse the output, all through just interacting with the environment.
So it's basically poking around with bash commands, trial and error, just to figure out how something like a make test command works.
It is. And yes, that costs compute. A human could read a README file in 10 seconds. But the payoff is total autonomy. Once it learns that skill, it never needs a human to write a README for it ever again. It's a huge investment in independence.
Incredible. And this is all one single LLM policy doing the work, but it's split into two different roles, right? This is where the self-play part comes in.
That's right. It's one policy. The parameters are shared, updated together through reinforcement learning. But we prompt it to act in two adversarial roles. First, you have the bug injection agent. That's the challenger. Its job is to create the hardest problem it can think of. And then you have the bug-solving agent, the solver, whose job is just to fix it.
Okay, so let's look at what the injection agent actually creates. This homework it gives itself. It's not a normal bug report.
No, it has to be completely machine-readable, formally specified. The sources call it the bug artifact, and it's a collection of 5 critical files that define the whole problem.
Okay, walk us through those 5 files.
First, you've got the heart of it, the buginject.diff. That's just a standard Git patch that introduces the bug into the code.
Simple enough.
Then you have the parts it discovered itself, the testscript.esh, which is the command it figured out runs the tests, and testparser.py, a script it writes to turn the raw test output into a clean JSON summary, mapping test IDs to pass or fail.
Okay, so those 3 define the bug and the testing environment. What are the other 2?
The fourth is just testfiles.txt, a list of the test files it's using, but the 5th one, testweaken.diff. This is the really clever bit.
Test weaken. So the agent intentionally creates a test gap. Why would it immediately weaken the test it's just figured out how to run?
Because that's what makes the challenge realistic. The testweaken.diff is a patch that literally removes or weakens tests to hide the bug from being found easily. It simulates a real-world scenario where a bug slips past a weak test suite.
Ah, I see.
But here's the genius part. The reversal of that weakening patch is what formally specifies what the fix needs to do.
Okay, so you're saying the act of removing the test actually defines the solution. You don't need to write, the code should do X. The specification is just fix the code so that when we add this test back in, everything passes.
Exactly. It completely replaces the natural language issue description. It provides a formal, non-ambiguous goal for the solver.
Okay, so the bug is defined. How do you make sure these bugs aren't just, trivial syntax errors? That they're actually high-quality, meaningful problems?
Right. So before anything is handed off, it has to pass these really rigorous consistency validation checks. It's a quality control step.
And what does that involve?
First, the tests have to pass on the original clean code base. Simple baseline. Second, after you apply the buginject.diff, at least one test has to fail. Third, the weakening patch has to work. After you apply test_weaken.diff, that failing test has to start passing again.
So you're confirming the patch successfully hid the bug.
Precisely. And then there's the most advanced check, which they call inverse mutation testing.
Okay, that's a term we need to break down.
Yeah, so traditional mutation testing checks the quality of your test suite. This inverts it to check the quality of the bug. It verifies that every single line of code changed in the bug patch was necessary to cause the failure. If you revert one part of the change and the test still fails, that change was just noise.
So it ensures the bug is focused, not just a bunch of random edits that break things.
Exactly. Tight and focused.
That handles quality.
Yeah.
What about diversity? How does it avoid just creating the same easy bug over and over?
They use two main strategies for that. The first is what they call a removal-oriented bug. The agent is specifically told to just remove chunks of code, or even entire files.
And that forces the solver to do what?
It forces the solver to actually reconstruct functionality from scratch. It requires a much deeper, almost architectural understanding of the code. It's not a simple one-line fix.
I see. And the second strategy?
That's the history-aware bug. This is really cool. The injector agent actually browses the repository's Git history using commands like git log, and it finds old bug fixes and reverts them.
Oh, that's clever. It's recreating realistic bugs that actually happened before.
Exactly. It generates bugs that look just like things human developers face after a bad merge or rollback. And critically, it has to apply little compatibility fixes to make sure the project still runs, so the bug is a subtle, logical error, not just a crash.
So once you have this high-quality validated bug, the solver agent takes over. It gets the buggy code, but I remember you said its Git history is wiped clean.
Yep, has to be. Can't let it cheat by just looking at the history to see what the injector did. That information leakage would ruin the training. The solver just gets the broken code and the formal goal. The reverse test weakening patch, that's its only instruction.
And of course, failure has to be part of the learning process.
Yeah.
What happens when the solver just can't fix it?
Failure isn't thrown away. It's actually leveraged into a new training opportunity. They call them higher order bugs.
Training.
If the solver's first attempt to fix the bug fails, the system takes that failed fix, which is now buggy code itself, and turns it into a new layered challenge. It's a way of mimicking how human developers sometimes introduce new bugs while trying to fix old ones.
How many layers deep do they go?
The paper only explores first and second order bugs. Any deeper, and you risk the new bug colliding with the original one in a confusing way, so you don't get a clean learning signal.
Right, so this whole thing is set up like a game. The solver wants easy bugs, the injector wants hard ones. Let's talk about the reward system that manages that tension.
The rewards are opposing, yeah. The solver's is dead simple. +1 for success, -1 for failure. It's incentivized to solve as many as possible, so it wants easier problems.
But the injector's goal is way more complex. It's not just create a bug, it's create the perfect learning bug.
Exactly. The injector's reward is designed to find what you could call the Goldilocks zone of difficulty. It gets the maximum reward only when the bug is challenging, but still solvable.
So if the solve rate, let's call it S, is between 0 and 1.
Right. If the bug is trivially easy, so S equals 1, or impossibly hard, where S equals 0, the injector is penalized heavily.
That's fascinating. So the injector is always pushing the solver right to the very edge of its abilities. What did the analysis show as the ideal difficulty?
This is the really counterintuitive part. For the injector to maximize its own reward, it has to aim for a target solve rate of only about 20%.
20%. So it's actively trying to create a bug that the solver will fail on 80% of the time.
Yes. Because it knows that the 20% of the time it succeeds, that success provides the maximum possible learning gradient. It's not about easy wins. It's about hard-fought lessons. This adversarial pressure creates a constantly evolving curriculum that gets harder as the solver gets better.
An online curriculum generator. Okay, so let's get to the results. Did it actually work? Did the self-play training beat training on human data?
Yes, and by a lot. Substantially better. SSR was evaluated on 2 really tough benchmarks, SWE Bench Verified and SW Bench Pro.
These are complex, real-world problems.
Very. And using the same base model, the SSR agent consistently and substantially outperformed the baseline that was trained on human data across the entire training run.
Give us the numbers on that.
On SWE Bench Verified, the improvement from self-play alone was plus 10.4 points. On the harder SWE Bench Pro, it was a plus 7.8-point jump. And remember, these agents were evaluated on natural language bug reports, which they never saw during training.
Which proves it's a generalizable skill. It wasn't just learning to solve its own little internal games.
Exactly. It learned how to fix bugs, period.
And the ablation studies, did they confirm the whole loop was necessary?
They did. Training just the injector or just the solver was way worse. You need the full cycle. And the bug injection strategy really mattered. Just telling it to write a bug gave you superficial stuff. The removal and history-aware methods were what generated the rich learning signals that led to the big gains.
This sounds like a genuine breakthrough. But what are the catches? What are the big limitations or future directions they point out?
The paper is very clear about this. The biggest limitation is its total reliance on unit tests for verification.
And unit tests are only a piece of the puzzle in real-world software.
A small piece. If the tests the agent discovers or creates don't actually cover real user behavior, then the agent is just getting very good at passing a narrow artificial test suite.
Okay, what else?
There are also the theoretical risks that come with any of these self-play games, the fear of a dominant challenger.
Meaning the injector finds a way to cheat?
Essentially, yeah. It could find a way to hack the reward function, maybe by creating bugs that are so obfuscated they're impossible for the solver to understand, or by creating tests that fail randomly, which would just destabilize the whole game.
So that's the big question. What stops the agent from just getting good at winning the game instead of getting good at coding?
And the researchers argue the solution is strong grounding. By forcing the agent to operate in these huge, complex, real-world code bases, you constrain it. You keep it focused on realistic problems, which seems to prevent it from just going off and exploiting the rules of the game.
So this deep dive really shows a clear path forward. LLMs moving beyond just copying human developers to autonomously gathering their own experience, designing their own curriculum.
It's a huge step. We're watching the transition from a coding assistant to a self-sufficient, self-improving engineer. This suggests a first real step towards systems that can actually exceed human capabilities in software purely through their own self-directed learning.
A final thought for you to chew on. If we want these agents to solve really massive tasks, I'm talking about building whole new software stacks from scratch or migrating an entire enterprise system, the current unit test verification, even if it's self-generated, probably isn't enough. So this raises the big question. Will the next breakthrough require an agent that can verify its own work not against a list of tests, but against a high-level, complex goal described in natural language? That's the challenge for the next generation of these AI engineers.